Hello and welcome to our web series on passive fire protection. My name is John Henry and I'll be your host for this series where we're going to look under the hood of all things passive fire protection, specifically for service penetrations. We're going to look at what it is, why we do it, what the building code regulations are, the fire testing standards AS 1530 Part 4 and much more. So stick around and let's see what we can learn. In this series, we're going to be covering a lot of information. So there's an introduction to passive fire, the building code, and in this case, we're looking at NCC 2022, the requirements for passive fire. We'll look at AS 1530 Part 4, the fire testing standard. We will look at the definitions of FRLs and RASF ratings. We'll look at deemed to satisfy compliance paperwork, interpreting the building code and avoiding common mistakes, and planning ahead for service penetrations, the do's and don'ts. So without further ado, let's get stuck into episode 1, Introduction to Passive Fire. As a quick introduction to Trafalgar Group, we are a manufacturer of passive fire protection systems, proudly Australian owned, and we have over 500 Australian made products in our range, which we're really passionate about. Not just the passive fire, but the Australian manufacturing as well. Today we're just looking at the passive fire systems, but if you are interested in the other options we have, feel free to check out www.tfire.com.au. So let's start with a definition of what is passive fire protection. So passive fire protection exists to contain or slow down the spread of fire by compartmentalizing a building into fire-resistant zones using fire walls, floors, ceilings, and doors. What we're trying to do is keep the fire in its fire compartment without it spreading to adjacent compartments. And the reason we do this is for life safety. We want it safe for people to be able to escape the building, use the fire escapes and passageways to get away from the fire. We also want it to be safe enough that the fire brigade have confidence that they can get into the building and extinguish the flames in that certain fire compartment. The other reason we do it is also to obviously bring down the cost of insurance claims when it comes to fire damage. If we can reduce the amount of damage from the start, it should help reduce the insurance across the entire buildings. Let's take a look at a video of what we're quite up against with passive fire protection. So this is an interesting video that is available for free on YouTube. That shows a living room where a fire source has been set up in the corner. Now this could be a phone charger or a Christmas tree or a heater, something that may have malfunctioned and caused the fire to ignite. And what this video really demonstrates is how quickly the fire can spread from just a small source in the corner to enveloping the entire room. This will give us a good understanding of what fire compartments are and why they're very important, especially when you get to multi-story buildings. So after 1 minute, the fire has spread from the initial source now onto the couch. And you'll see on the right hand side, there is a door and a corridor. So imagine this, if you will, as several stories up in a high-rise apartment building. This might be someone's apartment and that's the corridor to get down to the fire escapes. Now what you'll start to notice is a bit of a smoke layer developing towards the ceiling. And that's all the smoke coming off the fire, grouping around the ceiling as it gets hot and more buoyant than the ambient air in the room. So at 2 minutes, the fire has already doubled in size. And that's why they say if there is a fire, you should get down low and go. You shouldn't bother trying to get any of your valuables. You just got to get yourself and your family out of the building. What's going to happen now is the fire is going to start to generate so much radiant heat that it's going to start to evolve gases, volatile gases out of other elements around it, like the couch cushions. And this video is really great. It'll zoom in on the couch in a minute and you'll actually see those gases coming out. And what happens is those gases then contribute to the fire, which then present more gases, which then present more heat, more radiant heat, which will then run away almost exponentially. And there it is. So now at 3 minutes, the fire's become so hot that even some of the unburnt particles in the smoke are starting to ignite and contribute. And at that point, pretty much everything combustible in the room is going to start to ignite. And we call this a flashover. So at 3 minutes and 10 seconds, the fire brigade then step in to extinguish the flames. So you can just imagine if that was a fire compartment, that fire is going to remain trapped in there and it's not going to be able to spread to the corridor or adjacent apartments or into the fire escape. So people can get out through the building, and in theory the fire brigade can come in with some confidence that the fire is going to be contained to a certain part of the building to be able to put it out. Now, it should be noted when we talk about passive fire protection that we do not consider the intervention of active fire protection. So when we do our fire testing, when we develop the systems, we have to assume that they need to work without any sprinklers or active intervention. And that's a good segue into what sort of fires we are designing against. So on this slide, you'll see the time temperature graph that's given from AS 1530 Part 4. AS 1530 Part 4 is our fire testing standard, and it has this time temperature curve that has a model of a cellulosic fire, which basically means organic materials like timbers and cottons, based off research that's been done for many, many decades. This is the global adopted ISO curve that's used to model building fires. So it starts at ambient temperature and pressure, and as the fire starts to develop, you'll see the temperatures tick up from ambient all the way up to, say, at 10 minutes, you're at 659 degrees, at half an hour, 821 degrees, all the way up to 120 minutes, or 2 hours, you're over 1,000 degrees Celsius. Then, of course, you can keep running the test to model longer fires. Up to 4 hours is the highest in our Australian code, but there are some international standards and codes that do keep running past 4 hours. It should also be noted that you can do other fire models. So the red line here indicates a hydrocarbon fire. In this instance, you could picture perhaps a car tunnel where you might get lots of fuel load from cars and trucks, which is your hydrocarbon fuel. These fires are obviously a lot hotter. So when you're designing a tunnel, you have to assume, or you have to design for the worst case that you've got. Now, the red line here for hydrocarbon fires is only really relevant for tunnels and other special projects. It isn't actually in the building code. We'll just be focusing on the black line, the cellulosic fire curve, for today's slides.